That's too hot. I think that's a good analogy. Yeah, I'm gonna re-record this sucker here today. I think I'm feeling like I can do a better job. So yeah, today's 22222, and I think that's worthy of writing down. The TV is clearly on. You just need to get your, there it is. Sorry. So yeah, today is 22222, and yes, it did fall on a Tuesday, which is absolutely remarkable. So 22222, and today is Tuesday. Oh my gosh. Absolutely mathematically. There are people that study numbers and how they're related to occurrences in the world. They're called numerologists. And I bet today is just a real special day for the numerologists of the world. Anyhow, we are solving more log equations. And once again, today, these log equations will involve quadratics. And so they come at you from sort of a new perspective, though. The quadratics will occur. However, they will occur for different reasons than they did before. So again, we're going to stick to simplicity here today. I really want to get through this lesson in less than 15 minutes, so we will not discuss imaginary numbers or odd sorts of hypotheticals during the course of the lecture. We will hold off on those. So we're going to assume we're working within the real number realm, and that is that, okay? So the idea today is, as we create our equations, again, we get quadratics, but we get them from a new place. And so there's really no point in belaboring this. We're just going to start with examples. And so the first example is going to be a log with a base that's algebraic, a base of x plus 4. And the argument of the logarithm will also be algebraic, 2x squared minus 7x. And then the logarithm itself will equal 2. There is no condensing in today's lecture. If you're still on last night's homework, then you still have to go and do some more of that. But for today, there is no condensing at all. You're given exactly what you need to do the water cycle diagram. Every problem is just ready to rock and roll. So we're going to, I'll continue to draw it because I think it helps. I'm going to take this to the power of this and set it equal to this. Over and over and over and over again. So in its raw form, it says x plus 4 to the power of 2 is equal to 2x squared minus 7x. Now, I'd like to do this a couple different ways, and then going forward from this point, I'm going to go a little quicker. So I'm going to show you a couple things that you need to know here. You already know them both. I'm more showing them to you to bring them back to the forefront of your memory. But if I take this x plus 4 squared on the left-hand side, I'm going to just show you, I'm going to switch colors and write over here in yellow for a minute. If I do x plus 4 times x plus 4, don't forget, that's what it means to take x plus 4 and square it, right? We will not say something terribly unforgivable like x squared plus 16. We know it's not that easy. That's like ignoring half the problem that has to be done. So when I do x plus 4 squared, I get x squared plus outside 4x plus inside 4x plus 16. You need to speak up if you don't know where I got any of those from. In the future, I'm not going to show those steps. I'm going to go quicker, and I'll show you how to go quicker as well. So what that becomes is x squared then plus 8x plus 16. Got it? I'm going to give you a second to write that down, and then I'm going to show you how I think we should be actually squaring binomials. It's called square, square, multiply, double, and it's a lot quicker. It's the same thing, it's just quicker. Everybody got that written down? Okay, let's start the process over, but go quicker. This time I'm going to switch colors and do it in red, because I think it's, actually, no, I'm not going to do it in red, because I'm going to need red for something else. So I'm going to write the problem over here as x plus 4 squared. And I'd like you to get to a point where you start doing these in your head quick, like 5 seconds, boom. You don't have to show work on them. So I'm going to color code them. I'm going to call this guy Mr. Red. I'm going to call this guy Mr. Blue. And this is how you square binomials in your head, and you do it quick. What is red guy squared? What is blue guy squared? Now I want you to notice that I'm going to leave a space. You've seen me do this before in math where I leave voids, and I do it on purpose because I need to put something in there. Now, if you take right now red guy times blue guy, just red guy times blue guy, what do you get? You get 4x. Double that, what do you get? 8x. And that is how you square a binomial in your head. Square, square, multiply, double. Got it? We'll practice that some more. Anyhow, what we need to know right now is that this problem can be rewritten now as x squared plus 8x plus 16 equals 2x squared minus 7x. So we've left the land of logarithms, and we're now back into an October problem. It's a quadratic equation. And should I move all of my stuff to the left, or should I move all of my stuff to the right? There is a correct answer. If we move it to the left, we're going to face a problem. And I'm going to do this, and I don't want you to do this with me. I consider this a mistake. It's not a mistake that we can't recover from, but it's a mistake because of something that happens. What's 1x squared minus 2x squared? I'd rather avoid having to factor something that leads off with a negative. Could I conquer that? Sure. I just rather, like, why put myself through it? So when I talk about should I move everything to the left or to the right, I'm asking you that question in the context of where will the x squared not go negative? Having said that, I'm saying x squared, head east. 8x, head east. 16, head east. You're all going that way just because I want x squared to stay positive. Having said that, if I subtract x squared across to this side, I am left with a beautiful single 1x squared. If I subtract 8x, what do I have? Nice job, Tanner. Negative 15x. And if I subtract 16, what do I have? Nice. And that's how we execute the setting it equal to 0. It's not a brainless process. We want to be aware of keeping x squared positive. And then just like yesterday, we're going to factor. And if you struggle to factor, then I'm just sorry. You got to come in and practice and get better. It's not going to go away. You take math classes, you got to know how to factor. So tell me about my signs. I agree with you. And what numbers do I want? Again, I agree with you. I'm agreeing with a lot of what you say today, Holmes. Good job. So those are my factors. And my solutions then come from the factors. What solution do I get from there? Yes, very good. And then I will just tell you to kind of maybe hopefully cut this lecture a little shorter. You're going to be expected to just briefly go through and check your logarithms again for negatives. And so going back to the beginning, look up in your notes about 4 inches. What was the original in the log of what? Log of what? No, that's the base. The argument of the log was the 2x squared minus 7x thing, right? So just take your answers real quick, stick them in there. You'll see that they both come out positive. And I've been trying to do some reading on the validity of a negative argument of a base. And I can tell you a couple things. Number one, again, quickly, I'm addressing this and I'm moving on. If you leave the realm of real numbers, you can work with log with a negative base. Yours, that's not going to be an issue. So you do not have to check the bases of your logarithms for positivity because they will all be, I assure you. Got it? And I know we're chomping at the bit and we want to ask, but we're going to wait on that one, right? So just plug them into the arguments of the log, make sure you're good to go. I haven't seen any issues with any that don't work, quite frankly. So you should be good. All right, let's head on to example number 2. Example number 2 says log base x of 9x minus 18 equals 2. Again, there is no condensing today. It is just water cycle diagram. So what is the next converted equation going to say? Good job, Logan. That's just perfect execution. Base to the 2 equals argument over and over and over and over again. This time, should I move all my stuff to the left or to the right? To the left this time, because that's where the x squared says, oh, I'm already here and there's no one else like me. So you guys just come over here because I'm positive. So this is the cool side. So x squared stays. What comes after x squared?
Negative 9x, positive 18.
Perfection. And then we set it equal to 0. And again, it's time for factoring. And the factoring, this ought to be pretty rudimentary factoring for you guys at this point. Tell me about my signs. Both negatives. And what numbers am I looking for? What'd you have for breakfast today, Tanner? Do you normally eat breakfast? Well, based on how you're just kicking my class's butt today, I'd say you should probably keep skipping breakfast, bro. You're crushing it. All right, so -3 and -6, they multiply to make 18. They add to make -9. They're a perfect pairing. And so my answers would be x equals 3, and of course, x equals 6. Again, I'm skipping because we learned this yesterday. It's on you to plug those numbers back into the argument of the logarithm to make sure everything is fine. Okay. Example number 3. Yeah, Xavier.
Indicate. Wait, in the last example, x equals -1. But what about the log base? Log of x. If it was like -5, would the base of the log make any difference?
It does. I'd say that there's a possibility of logs with negative bases. You should Google it after we get done, finish your assignment, and Google can logs have negative bases. You might be surprised by the complexity of the question. Your logs will not have negative bases today.
All right.
All right, good enough? All right. So this example is going to be just a little bit harder only on the front end though. Like once you survive the log step, the quadratic itself is, whatever, it is what it is, we factor. So we have a log with a base of 2x minus 5. And the argument of the log is 3x squared minus 7x minus 11 equals 2. Now this gives me a chance to skip a step, and I don't want to do it to alienate anybody. I more want to do it to try to encourage you guys to see how much more efficient we can become as mathematicians. So I'm going to do something. Watch out. I'm going to write 4x squared minus 20x plus 25 equals 3x squared minus 7x minus 11. Now, I realize that I just tried to, quote, save time, when in reality, I'm going to still go back and explain how I got it. But I just want you to kind of embrace the idea that I can be quicker. And where I got the 4x squared minus 20x plus 25, I'll write it in yellow, just kind of right here in the center, was I did 2x minus 5, and I raised it to the power of 2. And then I used that shortcut we learned about 7 or 8 minutes ago, that square, square, multiply, double. So remember, let's just think of them as red guy, blue guy. Here's red guy. Here's blue guy. What's 2x squared? 4x squared. Jackpot. What's -5 squared? Jackpot. And then again, take the red guy and the blue guy, just the things in the circles, and multiply them together. What do you get? You get -10x. Double that, what do you get? -20x. So you can start doing that on a quicker click without having to write it all out. So anyhow, here we arrive in Quadraticville. Should we move everything to the left or to the right? To the left, for sure. Because if I subtract the 3x squared across to the west, then I'm ensuring myself that the x squared will not go negative. I like that. So I'm left with just 1x squared. How many x's will I have? And don't you dare say -27. -13. Nice job. And then I got to add the 11 across, and what do I get? Yes. And here, for the, I don't know how many, 20th, 30th straight time, we wind up with a factorable quadratic expression set equal to 0. And so it's going to factor into a pair of these, x, x. My signs are, of course, both minuses. They are 9 and 4. Rendering the solutions the things that make the parentheses equal 0, in this case, namely 9 and 4. I have one more example. The reason I'm re-recording this lecture is because I ended my lecture here first hour and I realized I left something out. And so I'd like to add this back in for your notes. And I don't think anyone from first hour would ever rewatch the lecture, but I just would like to have it on record that it was my bad. So this last problem is log with a base of x plus 3. The argument of the log is 2x squared minus 5x plus 9. And it equals 2. So again, in the interest of trying to be efficient mathematicians, as I take the x plus 3 and I raise it to the power of 2, let's see if we can skip the middleman step. What do we get?
X squared plus 6x plus 12.
Oh, you almost had it. X squared what?
Plus 6x.
Yeah.
Plus 12.
Why are you saying 12? 3 squared
Uh,
plus 9. So again, where this came from was the x we squared to get x squared, the 3 we squared to get 9, and then when we multiplied the x and the 3 together, we got 3x, doubled it, we got 6x. And that's where that comes from. So we have x squared plus 6x plus 9 equals 2x squared minus 5x plus 9. And you might think, well, why are we doing this? This is just like the other ones. No, it's not. Should we move everything to the left or to the right? This time to the right, because it's where my x squared will be positive. So x squared I bring over and I'm left with just a singular x squared. I subtract 6x and I'm left with minus 11x. And this is the reason why we're doing a fourth example, because it equals 0. When you do minus 9 on both sides, to bring these 9s together, you're left with nothing, right? And so where normally here in this red box, we would have a number, we don't. And you knew how to do this like 5 months ago, and it's been a while, so I'm here to refresh you. This is a special kind of quadratic that when we factor him, we don't need 2 sets of parentheses and 1 plus and 1 minus and all that. We simply pull out the greatest common factor. It's been a while. It's been a long while since we've talked about this. But if you look at the 2 things that I'm underlining in blue, what is their common factor? It is x. And if I pull out that x, I am left then with x minus 11. And now I look at my factors not as like an x plus 5 and an x minus 2 or something. I just look at them simply as, okay, green guy. That's called a factor. This is the stupidest question anyone will ask you all day. What could you put in place of x to make the green jelly bean equal 0? So one of your answers is 0. Want you to be aware that this is a possibility. What could you put in place of x to make the yellow jelly bean equal 0? That one we're used to. So when you get to the end, if you get a quadratic that's missing its c term at the end, you kind of approach your factoring. Technically, you're doing the same thing. You kind of feels a little different because of how you do it. Okay? Yeah. Can I quit my recording before you ask this? Is that okay? Okay, good. I'm going to end this. And you guys, your assignment popped up on Delta Math.